So, a polynomial function cannot have more real zeros than its degree. And that makes sense, right? If we had a quadratic function, which is a degree 2 polynomial, you could see that it could have 2 zeros, it could have 1 zero, or it could have no zeros, right? This is what we know about quadratic functions that are degree 2. The same holds true for higher and higher degree polynomials. So for example, f of x equals 3x cubed plus 5, it could have at most 3, but it could have 3, 2, 1, or 0 zeros. For g of x equals x to the 7th minus that's 6 and so on and so forth, this could have at most 7 zeros. For x to the 13th minus 1, that could have at most 13 zeros, but it could have 12, it could have 10, it could have 11. And if I have f of x equals a to the n, x to the n, and so on, this is our formal definition of polynomial in case you didn't remember it, it could have at most n zeros. When given a polynomial, we can use the rational zeros theorem to determine what our zeros could possibly be if we don't know. So let's let f be a polynomial of degree 1 or higher, where each coefficient is an integer. If p over q, an integer meaning it has to be in the, it can't be a fraction, it can't be a radical, right? It's a whole number or their additive opposite. If p over q in Lewis terms is a rational zero, then p must be factors of a sub naught, and q must be factors of a sub n. So let's take a look at what this means. So, okay, if I have f of x equals 3x cubed plus 8x squared minus 7x minus 12, I want to take all my possible p's, which are the factors of 12, and all my possible q's. So I need to take factors of our constant and factors of our leading coefficient. So some of the factors of 12 would be 1, 2, 3, 4, 6, and 12. But we have to make it plus or minus. Some factors of q would just be 3 and 1. So if I take all of the factors of p over q, 1 over 1 gives us 1, 2 over 1 gives us 2, 3 over 1 gives us 3, 4 over 1 gives us 4, 6 over 1 gives us 6, and 12 over 1 gives us 12. I then have to do the same but over this 3 here. So 1 over 3 gives us 1/3, 2 over 3 gives us 2/3, 3 over 3, well that's just 1, so that's cool. 4 over 3 gives us 4/3, 6 over 3 gives us 2, and 12 over 3 gives us 4. So these are all the possible potential rational zeros. I'm not saying each of these are a zero, right? Because this can have at most 3 zeros, but this gives us a place to start and figure out which 3 of these are indeed the zeros of this cubic function. So why don't we go ahead and practice listing the potential zeros of f of x equals 2x cubed plus 11x squared minus 7x minus 6. So let's list our p's. Those are going to be the factors of our constant, a sub naught. So the factors of 6 are 1, 2, 3, and 6. Those are all the possible factors. My factors of q, which are 2, which is 2, are just 1 and 2. I then need to take all possible combinations of p over q. So 1 over 1 gives us 1, 2 over 1 gives us 2, 3 over 1 gives us 3, and 6 over 1 gives us 6. I now have to take all my possible p's over 2. 1 over 2 gives us 1/2, 2 over 2 gives us 1, which we already have, 3 over 2 gives us 3 halves. And 6 over 2 gives us 3, which we already have. So here are all the possible zeros of this polynomial. I did go ahead and type up all the possible zeros so you could check your answers from the posted PowerPoint. And you might think, oh, this is great. So now I know all the potential zeros, but how am I going to determine which of these are the 3 zeros, at most 3 zeros, I'm going to have in order to factor this polynomial? So let's go ahead and go over a few steps. So how would I have found the rational zero, the real zeros of the function we were looking at earlier, which is 3x squared plus 8x minus 7x minus 12. I don't know why these symbols aren't transferring over. Sorry, guys. So the first thing I want to do is I'm going to use the degree of the polynomial to determine the maximum number of zeros. Since this is a degree 3 polynomial, I know there's at most 3 zeros. The next step is I'm going to use the rational zeros theorem to identify my potential zeros. That's what we did a couple slides ago. So we found all of our potential zeros to be plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 12, plus or minus 1/3, 2/3, or 4/3. That's a lot of possible zeros. Oh my gosh. Okay. So we're then going to use the factor theorem to determine if each potential zero is a zero. Remember, if it's a zero, f of c equals 0. We're going to use the factor theorem. If it is, we can then use synthetic division or long division, but synthetic division is simpler and it's a little bit faster in order to factor our polynomial. And we can repeat that process until we've fully factored the polynomial. I recommend when you get something of the form of a quadratic that you can either use the quadratic formula, it's a little bit faster, or find the factors of AC that add to B. That's my favorite way. And I'm sure you guys are shocked to know that that's my favorite way. So what we could do is we could go ahead and do some synthetic division for -1, and we get that, we pull down our 3, -1 times 3 is -3, 8 and -3 is a +5, -1 and 5 is -5, and that's a -7. -7 and -5 is -12, -5 times -12 is a +12, and we add those together to get 0. So my remaining polynomial would be f of x equals x plus 1 times 3x squared plus 5x minus 12. And then I could factor this. Okay, what are the factors of AC that add up to B? Well, the factors of AC that add up to B would be a good way to factor that, or you could use the quadratic, and we find that it becomes x plus 1, x plus 3, and 3x minus 4. So now I have all of this, and I can set all my factors, and I could set it equal to 0 to determine what my zeros truly are. And I would get that my zeros equal -1, which is the first one we found, -3, or +4/3. So let's go ahead and find all of the real zeros of 2x cubed plus 11x squared minus 7x minus 1. So let's start at the very beginning, and a very good place to start is with 1. So if I take 1 into my polynomial, which is 2, 11, -7, -6, I pull down a 2. 1 times 2 is 2. 11 times 2 is 11 and 2 is 13. 1 times 13 is 13. -7 and 13 is 6. 1 times 6 is 6. My remainder is 0. Aha! So now I have the polynomial f of x equals x minus 1 times 2x squared plus 13x plus 6. And I say, okay, what are the factors of 12? AC is 2 times 6, which is 12, that add up to B, which is 13. So I can rewrite this as 2x squared plus 12x plus 1x plus 6. And now I can factor by grouping. Don't forget your x minus 1. Factoring by grouping, I have f of x equals x minus 1. The greatest factor of 2x squared and 12x is 2x. The greatest 2x, and that becomes then x plus 6. The greatest common factor of 1x squared and 6 is just 1. So my polynomial fully factored is x minus 1, 2x plus 1, and x plus 6. So in order to factor this, I have to set each of these equal to 0. And I'm going to do that up here in green. So x minus 1 equals 0, so I have x equals 1. That's one of our zeros. 2x plus 1 equals 0. I subtract 1 from both sides. I get 2x equals negative 1, so x equals negative 1/2, which was indeed one of our possible zeros. Then I have x plus 6 equals 0. So I have x equals negative 6, which is again, this is a typo. This is in our list of possible zeros. Our possible zeros were, if you look back at the previous slide, positive 1/2, positive 1, positive 2, positive 3, positive 6, positive 1/2, positive or negative 1/2, and positive or negative 3/2. And I will fix that in the future PowerPoint that I upload for you guys. But our real zeros that we found were also part of the possible rational zeros that we had found. So here is our answer, and this one has the correct list of possible rational zeros. We could also check our real zeros by graphing. So if we go to Desmos, you know it's my favorite, and we enter our polynomial, which is f of x equals 2x cubed plus 11x squared. I'm sure you guys just love me reading equations out loud. Minus 7x minus 6. This is how I make a living as an ASMR video maker. Okay, so you can see that I found my zeros were negative 6, 1/2, and 1. So negative 6, negative 1/2, and 1 were my zeros that we had originally found.